So today we're going to look at variational inference. Just as a reminder, you should be working towards your homeworks, your second homework, also project proposals, and you should be working on your project. So today we're going to look at variational inference. I'll try to give you an intuition of what that is. And the next couple of lectures, we're going to look at Markov chain Monte Carlo based inference. So today's lecture is going to be a little bit more on the technical side. But nonetheless, I'll try to give you the overall idea of what that is. So what is approximate inference? We've seen this in deep Bayes machines. We've seen this in deep belief networks. And we're going to see it in a lot of other things, like variational autoencoders, for example. So when we're using probabilistic graphical models, we're typically going to be interested in evaluating posterior probabilities over some latent variable z given x. Okay? So think of z as h's, some hidden states, and we're going to be interested in figuring out what that posterior probability is. For example, if you've heard about expectation maximization algorithm, we need to evaluate the expectations of the complete data log likelihood with respect to the posterior distribution over the latent variables. We haven't looked at EM algorithm, but we're going to look at the version of this algorithm in today's lecture. So for more complex models, it may be feasible to evaluate the posterior. So, or compute expectations with respect to the posterior, right? And this is exactly what we've seen with deep Bayes machines and with deep belief networks, where we have to have some kind of approximate recognition networks that gives us some approximate posterior over the latent variables. And that's exactly the same thing for variational autoencoders as well. So this typically occurs when you're working with high-dimensional latent spaces or when posteriors have complex form, where we can't really compute expectations precisely or exactly. So for example, in Boltzmann machines, that is the case. Remember when we were looking, so that's why using contrastive divergence to estimate these expectations. In deep Bayes machines, we had to use mean field approximation to figure out what's the posterior distribution of the latent variables. So let's set up the following problems. The model may have latent variables and parameters, in which denote all latent variables or parameters by z. Typically in Bayesian frameworks, there is no difference between latent variables and parameters. Everything has you're trying to estimate some posterior distribution. We'll also denote a set of all observed variables by x. So for example, given a set of n ID data points, so x is a bunch of images, let's say a bunch of examples, and z is the bunch of latent variables, right? So for example, z's here could be the hidden states of an deep belief network. So probabilistic model specifies the joint probability distribution over the latent variables and observed variables. And our goal is to find approximate posterior over the z latent variables given x. And perhaps model evidence, P of x. Right? In some cases, if we want to be able to estimate log probabilities in Boltzmann machines, we need to be able to estimate what's P of x. Right, so for example, remember when we looked at deep belief networks. In this case, V is the observed data, think of it as x, and h's are the latent variables, think of them as z. Right? And deep Bayes machines, it's exactly the same way. So computing posterior over the hidden variables will be intractable, right? And the reason why it's intractable, because in both models, if I want to figure out what's the posterior distribution over the latent variables given the data, you can't really compute it exactly in either one of these models. So you have to resort to some approximations. Same thing happens in variational autoencoders. In variational autoencoders, we'll see these models in the future. You can't really compute the exact posterior over the latent variables. You have to resort to some approximations. Right? So the question is, what can we do here? How can we do proper approximation of this distribution? Because it's very complicated. It doesn't have a closed form solution. Right? Any questions? So in deep Boltzmann machines, for example, you have random variables which will contain both visible and hidden, right? And if we want to figure out what's the probability over V, that sometimes is called model evidence. In particular, if we want to evaluate this model on new unseen test examples, we need to be able to compute probability of V. But in general, computing posterior over hidden variables will be intractable. It should be double computing. It should be in general computing posterior over hidden variables will be intractable. Right? And that's exactly why. We can't really figure out what's the distribution, exact distribution of this random variable, just condition on the data. Because it depends on the states of hidden variables at the layer above. Inference is exact in restricted Boltzmann machines, right? You can compute the exact posterior, but in more complicated models, you can't compute the exact posterior, so we have to resort to approximations. We've looked at the variational bound, and this is one of the key factors for a whole lot of different models. In fact, any model where you have some complicated latent variables, either in layers or in other models, doesn't have to be deep network models. You have some likelihood, probability of x given the latent variables. Anytime you need to do learning in this model, you will need to be able to infer posterior over the latent variables. And so variational learning is one way of doing this. So let's look at the variational learning. Given the joint distribution, you can always specify the joint distribution, right? If you don't have the joint distribution, you don't have the model. So given the joint distribution observed in latent variables, governed by some parameters theta, the goal is to maximize the likelihood function with respect to theta, right? We really need to be able to sum out the states of the hidden variables, because that's what the likelihood objective is, right? If we could sum out the states of the hidden variables, we have a likelihood function. We can optimize the parameters to maximize the log likelihood function. The issue is that we have these latent variables, so this sum is exponential. Think deep Boltzmann machines or deep belief networks. You have to sum over all the states of the hidden variables in all the layers, and that sum is exponential. You can't do it. This is also a very general problem for a whole range of different models. When your latent space is high dimensional, and you can't really, if you work in continuous spaces, it could be high dimensional integral. You work in discrete spaces, it could be high dimensional sum. Typically, these are exponential sums. And this is also a very big problem in statistical physics, in statistics. A lot of people are trying to figure out, in fact, a lot of learning is based on being able to approximate exponential sums or large high dimensional integrals, right? So we'll assume that z is discrete, but the derivation is going to be identical if z actually contains continuous or a combination of discrete and continuous, right? You're just replacing sums with integrals. Not quite. If you talk to a mathematician, there is a very big difference of replacing sums with integrals, right? It has to do with measures and doing things properly, but for this class, at the end of the day, you can just replace sums with integrals and you should be okay in most of the cases. So for any distribution Q of latent variables, we can derive the following variational bound. So let's look at the variational bound, and then we'll look at the concept of variational bound. So we look at the log probability, we'll look at log of the sum, right? That's an equality. Then what we're going to do is we're going to multiply and divide by the function Q. And that could be any distribution over latent variables. You know, Q of z could be Bernoulli's. Q of z could be Gaussian's. Could be whatever, you know, if you're working with discrete variables, could be just a bunch of Bernoulli's. You're working with continuous variables, could be Gaussian. Right? As long as it's defined in the same space. I can multiply and divide by Q. Obviously, you have to worry about things like this Q can have measure 0 or assign 0 probability to the places where this is non-zero. Right? Because if this carries some probability and you divide by 0, that's not defined. So you have to be careful precisely, you know, not to have division by 0, but in most cases, Q will never be 0. It will assign some probability. And then you can apply Jensen's inequality, which is just, again, based on the fact that log is a concave function. You can basically say it's always upper bounded by this expression here. Right? So you're taking log and you're pushing it inside. The other way to think about this is you're basically saying that you can view this sum as an expectation with respect to Q of this quantity. Log of expectation is always greater or equal to expectation of the logs. Right? Again, that's just done by the concavity of the log function. Right? So now something interesting happens. You're taking expectation with respect to Q function of this joint. Right? Now, notice what happens. What happens here is that now you have the joint, which you can specify in many of the models. So you know what the form of this function is. You just have to choose Q in such a way that you can compute this expectation. Okay? So think of Q function as like approximating to the posterior, simple approximation to the posterior, and you're choosing it in such a way that you can compute these expectations exactly. And that's a trick, right? Notice the other thing is that if this Q function has some parameters in it, or you're searching through the family of Q functions, you have a very well-defined objective. You're basically saying, how can I find Q such that this bound is as small as possible, right? And if I have that, I can optimize, this with respect to these parameters, this objective. So at least I'm pushing on the on the lower bound. And I can also optimize with respect to these parameters. That's essentially what deep Boltzmann machine was doing. It's essentially what deep belief networks are doing. This is essentially what variational autoencoders are doing. They're all basically saying, how do I optimize Q and how do I optimize parameters so that I'm pushing this bound up? So it's a maximization problem over Q and a maximization problem over theta, right? Sometimes Q functions will refer to the encoder network or recognition network. And this model will refer to as a generative model because it defines the distribution over the input space. Okay? So sometimes these are called decoders or generative models, and the Q is called recognition model, encoder model. Okay, so variational bound, we've divided. We've shown that this has this form. It also has this particular representation because I can put the Q here and I can put it aside. Right? So I can write this in terms of the expected value with respect to Q of log of the joint. And this function is called the entropy. This is just the definition of the entropy. The first term is called expected complete log likelihood. The reason why it's called expected complete is because this is a complete likelihood. It has X and Z. And it's taking expectation with respect to Q. So think of this decomposition as Q function is guesstimates what your latent variables should be. And once Q function guesstimates what the latent variables should be, once you have the states of the latent variables, you can optimize this function with respect to theta. Imagine somebody like in your deep belief network, somebody came and said, you know what? The state of the hidden variables should be 1, 1, 0, 0, 1, 0, 1, and so forth. Right? If somebody told you what the states of the latent variables are, you can just plug those latent variables in and update the parameters of the model. Right? And that's essentially what the role of the Q function is. It's kind of like filling in the missing information. Once you've filled in the missing information, you can optimize the parameters. Right? And this also was the essence of expectation maximization EM algorithm that was developed in '77, I believe, by Dempster, Rubin, and someone else, I believe. It's a very sort of, you have the equations, but it also has this very intuitive idea that you basically have this proxy as a way of figuring out what your latent variables should be. Once you know what your latent variables are, you can update the parameters of the generative model. Right? So in encoder-decoder models, like in deep belief networks and deep Boltzmann machines and variational encoders, Q is like telling you, the recognition model tells you, given the data, what the states of the latent variables should be. And then you're updating the parameters of the generative model. And then you're updating parameters of the recognition model and updating parameters of the generative models. So you're updating both of them so as to maximize the variational bound. And H of Q is the entropy. Now let's look at the entropy for a discrete random variable X. Right? The entropy of a random variable is defined this way. Right? It's sum of a log, its expected value with respect to P log 1 over P. And the thing you need to know about the entropy is that distributions that are sharply picked around few values will have relatively low entropy. So sharply picked distributions have low entropy, and those that are spread more evenly across many values will have high entropy. So here's an example of histograms of two probability distributions over 30 bins. This has an entropy of 1.77. This has an entropy of 3.09. The highest entropy is going to be a uniform distribution, right? That's the distribution with the highest entropy. And then if you're working in continuous spaces, there's something that's called a differential entropy, and it's just defined in the same way, right? Except for in the continuous space. So let's come back to the variational bound. We have this expression. We can also look at the following decomposition. It's another decomposition to keep in mind. I can always write log probability, what I'm trying to optimize, as the variational bound plus, this is the definition of the variational bound, plus something that's called the KL divergence. It's a Kullback-Leibniz divergence between Q and P, also known as relative entropy. And if you think of KL divergence measures, you can think of it as a measure of distance between two distributions. It's asymmetric, it's not symmetric, but it's always non-zero. So it's always positive. And KL divergence between Q and P is going to be 0 if and only if P is the same as Q. So if you manage to pick up Q distribution that matches your true posterior, then your lower bound becomes tight. You're actually optimizing the likelihood objective. So if you actually trace back to expectation maximization algorithm that heavily been used in statistics, in many of those cases, when you compute the posterior distribution, your posterior distribution is actually exact posterior. And if it's exactly posterior, then the bound becomes tight, in which case you're optimizing the likelihood objective. If the bound is not tight, so this distance is non-zero, then you have some slack or some delta. But that's the other way to think about this, right? Because the way you can think about this, you can think about optimizing the log probability either by maximizing the variational bound or by minimizing KL divergence, right? Some people think of, how do I minimize KL divergence between my approximation to the posterior distribution versus the true posterior, versus, so the two are equivalent. So yes, it measures the distance between the two distributions. So let's derive that this is indeed the true. And the way to derive this is really very simple. You're just writing the log of the joint as the log of the posterior plus the log of the marginal. You can plug it in the definition of the variational bound, and you get the result. You'll get the result that the log probability, marginal log probability, equals to the variational bound plus KL divergence. It's a very simple, very trivial way of doing the derivation. And the bound becomes tight if and only if your approximation to the latent variables equals to the true posterior. Right? If it's true posterior, the bound becomes tight. So that in this case, if it's equal to the true posterior, then the KL divergence would be 0. And you can see if the KL divergence is 0, then the low bound and the log probability, the marginal log probability, are the same thing. So for those of you who've taken, graphical model courses or introduction to machine learning courses, for those of you who've looked at models like mixture of Gaussians, for example, mixture-based models. In mixture-based models, you can compute the posterior of a mixing components exactly. You can get the true posterior. In which case there's algorithms, iterative algorithms of optimizing the actual log probability of the data. And obviously, if the KL is non-zero, it immediately follows that the marginal log probability is always upper bound by the variational bound, just from this equality alone, right? Because if KL is non-zero, positive, then you have this inequality. So that's the other way to derive the variational lower bound. So you don't have to use Jensen's inequality. So really, you have this decomposition, which is log probability of data is decomposed into the variational bound and the KL between Q, your approximating distribution, and the true posterior. So in terms of optimization, you either can think of it as optimizing the variational lower bound, or you can think of it as trying to minimize the gap between your approximation to the posterior and what the true posterior is. Right? Does that make sense? Okay, now, so we can decompose this marginal log likelihood at the variational bound plus scale between Q and P, and we can maximize the variational bound with respect to the distribution Q, which is equivalent to minimizing the KL divergence. So our optimization problem is going to be maximizing this variational lower bound. So which is kind of interesting, because what that means is that inference and learning can be phrased as an optimization problem, right? You choose the family of the Q distributions. Once that choice is given, you have the bound, the variational bound, and you're just optimizing this variational bound. So the whole learning is set up as an optimization problem. The other way to do it would be to use sampling-based algorithms. We'll see in the next lecture, you know, what the sampling-based algorithms are doing. But these algorithms are sometimes, you can form it as an optimization problem. You can look at the variational lower bound. You can evaluate it, and you can really see it's increasing. One thing is that these kinds of methods came from statistical physics, like midfield approximation and beta free energy approximations and so forth. They came to us from statistical physics because, you know, there people needed to compute expectations and needed to figure out what these posteriors are in sort of tractable way. So this is where a lot of this work is borrowed. The problem with variational learning in general is that once you've made a choice of the Q distribution, think of it as like a recognition network in your deep belief network. Once you made a choice of Q, if it's not flexible enough, there is always going to be gap, right? You will never compute the correct posterior. It's only going to be approximation, right? And there is an alternative view, which is maybe we can use Markov chain Monte Carlo based methods, again, which is something that we'll cover next class. In Markov chain Monte Carlo based methods, you have a theory that says that if you run your Markov chain long enough, I can prove to you that I'm going to be sampling from correct posterior. So in expectation, I will give you the right answers, right? And so now there is this argument. You know, statisticians don't like this framework because they say you can never get to the truth. Like, what's the point? But then there are also problems with MCMC methods, because you can be running these MC methods for years and they still might not converge to the truth, right? Whereas here you form the problem as an optimization problem and you just optimize it. So there are advantages and advantages to both, depending on what your viewer is. So if we allow all possible choices of Q, then the maximum of the lower bound occurs when your Q equals to the true posterior, right? So if you had a choice of choosing any flexible Q, then your best choice out of all possible functions would be to choose the true posterior, in which case KL is 0. For any other choice of Q, it's always going to be positive, right? Okay. So we can decompose into the marginal of likelihood plus KL, and we've seen some of the lectures when we looked at deep belief networks and deep Boltzmann machines, we sort of had this decomposition. We're going to make an assumption that the true posterior distribution is intractable. What we can do is we can look at the restricted family of your Q functions, right, or Q distributions, and then we'll find the member of this family for which KL is minimized. Once we choose a family over which we want to do optimization, then we can optimize the variational bound to find the best, the tightest bound. Right? We can do optimization of a Q to find the best one so that the bound is as tight as possible. And obviously, we have to restrict to the family of distributions that contains only tractable distributions, right? Because we can't really take Q and say it's another intractable model, because then we can't compute anything. Right? So it has to lie within the family of tractable distributions. At the same time, we want to allow some flexibility, right? We want to be able your Q distributions to be flexible. And that's why a lot of recent work is using these complicated neural networks as a way of parameterizing these Q functions, these recognition networks, and you want them to be as flexible as possible. Because if you have some simple, very rigid approximation to the posterior, you're not going to be able to learn anything useful. So one option is to use parametric distributions. And that's exactly what we'll see later in the class, and that's exactly what we've seen with deep belief networks and deep Boltzmann machines. We might have some approximating posterior over the latent variables parameterized by some parameters omega. And we're going to be optimizing over these parameters. And then the low bound becomes a function of omega of these parameters, and we can optimize the low bound to determine the optimal values of these parameters. And that's exactly what we've seen in deep belief networks. Your recognition model is like a stack of RBMs, right? So you have some recognition system. In variation encoders, we're also going to build this thing to be another neural network with its own parameters. Right? So you have your own recognition parameters that are just trying to push on the variational bound, and you're trying to approximate posterior as well as you can. The interesting thing also in terms of overfitting, you're not really sort of trying to overfit to the data. You're trying to approximate posterior. So the more flexible your model is, the better your approximation to the posterior will be, right? So this is kind of an interesting thing to think about. Okay, now here's an example of option to use parametric distribution. So let's look at the example in which the variational distribution is Gaussian, but we can optimize with respect to the mean and variance. So let's say I'm trying to say my posterior distribution is Gaussian, and I'm going to be optimizing for mean and variance. So let's say your original distribution is in yellow. The red one shows something that's called Laplace approximation. Laplace approximation is really basically saying find me the peak of the distribution maximum a posteriori, and then just use kind of Taylor expansion to fit a Gaussian to it, just to fit quadratic to it, right? Whereas if you use variational green approximation, this is going to be your variational approximation to that distribution. So you get to judge yourself which one is better. It seems like the green distribution captures a little bit more mass than the red one. Now, let's look at one particular factorization. It's called the mean field approximation. So we're going to consider restricting the family of distribution as follows. We're going to partition the elements of latent space into m disjoint groups. M could be individual units, individual variables, or could be groups of variables. Let's say we have m groups. So we're going to assume that the Q distribution factorizes with respect to these groups. Right? We're going to say our approximation is really independent product of these Q distributions. In the case of deep belief networks and deep Boltzmann machines, when you do mean field approximation, you're basically saying each variable is in its own group. So our posterior is just going to be product of of all the hidden units, and they're all going to be independent of each other. So we place no restrictions on the functional form of individual factors. We're going to be often denoting Q as simply QIs. So we're not going to say these QIs are going to be Bernoullis, or these QIs are going to be Gaussians, or these QIs are going to be Poisson. We're just going to say our approximate posterior is just going to be factorizing into these individual Qs. And the approximation framework, it's called mean field theory. So now, once we've chosen this family of fully factorized distributions, we're going to look for a distribution with the lowest, where the variational bound is maximized. Okay. So denoting QZ as simply QIs, we can look at the variational bound and write variational bound this way. Right? I'm just plugging in the definition of QZs. Right? Does that make sense? These are just logs. Just look at the logs, log QZs, they come out. That's what you're trying to optimize. And you try to optimize with respect to individual elements of QIs. What I can do is I can pull out QJ. All right? I can pull out QJ and say marginalized respect QJ, and then I pull everything inside. So this product is product of all the QIs other than J, because it's already pulled out over here. It's already pulled out over here. And the reason why I keep splitting is because they're all independent of each other. That's my assumption. If they were dependent, I couldn't do it. But because they're independent, I can push them out. Right? Plus some constants that don't really depend on this thing. So what I can do is I can say, you know what? I'm going to treat this as an expectation of QJ, this quantity here, where this quantity, I'm going to define what is this thing. This is an expectation of the joint with respect to all the variables other than J. Okay? And it turns out that I can actually compute this thing. The reason why I can compute this thing is because of these independence properties. So expectation of a bunch of factors that don't depend on each other, I can compute them. Because I can just compute them as, you know, bunch of products of individual expectations. So now I have this representation. So we take expectation with respect to the Q distribution of all variables, zi's, for which i's doesn't equal to j, so that I can compute this thing here. And again, the reason why I can compute this thing here is because I'm taking expectations with respect to Q variables that are independent. Right? If I'm talking about discrete random variables, then I just have to, for each random variable, I have to just look at the option 0, 1. If it's continuous variables, then I can just do one-dimensional integrals, which I'm going to make an assumption I can do. So you can compute this thing. Okay? Now suppose we keep these QIs fixed and optimize lower bound with respect to all possible forms of the Q distribution. Right? So I have this. What's the optimal choice of Q? Well, I can write this problem as this. This is just a simple derivation of KL term, right? So I can basically recognize, because the variational bound can always be written as the log probability of x minus KL. That's our equality. So I can put this inside and actually derive this KL term. So the minimum occurs, the optimal Q function is given by this expression. Because the optimal function is when KL equals to 0. Right? That's when the variational bound is maximized. Or I can take the logs and I can say the log of the Q is equivalent to this thing, which is something that I can compute, plus some constants. Right? Obviously, they have to be normalizable, so Q has to be a normalizable function. In fact, I don't think, sorry, it shouldn't be the same. It should be proportional, because if this is just, this has to be distribution, this is a distribution. So these are both distributions. So taking the log of the optimum solution for factor Qj is given by, you look at the log of the joint distribution of all hidden and visible variables, and you take an expectation with respect to all other factors Qj's or Qi's. Right? So the way you can think about this is that you take an expectation with respect to all the other variables, right? And you look at the log of the joint, and that's given by the optimal definition of the Q function. Then you can normalize it. You can exponentiate, you can normalize, and then you get the optimal Q distribution. Right? And these sets of equations represent the set of consistency conditions for maximizing, for attaining, you know, the lower bound. So you initialize all of these factors randomly, and you cycle through these factors, and convergence is guaranteed because the bound is convex with respect to each of the individual factors. Right? So I can optimize for each individual one, because this is an optimal solution. The problem is convex for each one of them. So you're kind of like doing coordinate descent, optimizing each factor in turn. And this is exactly when we looked at deep Boltzmann machine the other time, and we've looked at the variational bound, and I've mentioned that, you know, if you optimize it, you get a set of consistency equations. I'll show you again in today's class. This is exactly how you derive it, very much in the same spirit. So let me show you an example. Okay, let's walk through the example. So let's say you have a problem with approximating a general distribution by a factorized distribution. So let's say we look at approximating a Gaussian distribution using factorized Gaussian distribution. So let's say we have a two-dimensional Gaussian over two correlated variables, z1 and z2, right? So that's the definition of the Gaussian, two-dimensional Gaussian. And let us approximate this distribution using a factored Gaussian of the form, so the Q of z is just some factor of z1, some factor of z2. Okay? Does that make sense? So I'm going to approximate this two-dimensional Gaussian by a product of univariate Gaussians. And in general, you can see that if your model has some complicated, k-dimensional Gaussian or very large Gaussian, some complicated structure, you can always approximate it by the product of individual factors, right? In Boltzmann machines, you have multiple layers. You have some complicated posterior. You can approximate by the product of individual factors. In variational autoencoders, you price the Gaussian, so your posterior is going to be some complicated, but your likelihood is non-linearity. Your posterior could be very complicated, but you can approximate it by, again, product of individual Gaussian terms. So let's see how it works. Remember, log of the optimal one is just expected expectation of a log of the joint. So let's look at the expression for the optimal one. Okay, the expression for the optimal one is taking expectation with respect to Q2, right, of log of P of z, right, a two-dimensional Gaussian. So what is this two-dimensional Gaussian? Well, this two-dimensional Gaussian, if I write this up and I leave only the factors that depend on z2, that should be z2. Sorry, it shouldn't be z1. My mistake. And then there is another factor that also depends on z2. Right. So now I have, let's see. I have this expression, right, which is just I open the parentheses, I take the expectation through, and then you can note. Oh, no, I'm right. Sorry. You have to keep all the expressions that depend on z1 because this is a function of z1, right? So I'm trying to look at the log of the optimal for Q of the function of z1. So everything here that depends on z1. Everything that doesn't depend on z1, it doesn't really matter because we're not optimizing over z1. So we leave this thing. We have this thing, right? And I'm just taking expectations through. And notice what happens. I have to push the expectation over here, right? Because it depends on z1. I can't really toss it out. And so recognizing that this is a Gaussian distribution, you can basically say the optimal Q is going to be a Gaussian distribution with this variance and the mean that's going to be given by this expression. Right? So that's the optimal parameters for Q1 star. And the same way, you can actually compute the optimal parameters for Q2 star, and it's going to have pretty much the same form. And there are two observations to make. First of all, in this particular setting, we did not assume that Q is a Gaussian, but rather derived it by optimizing the variational bound of all possible distributions. We just made an assumption that the distribution factorizes. For the model figures out that the optimal distribution is the Gaussian. That is the case for a lot of variational learning. The solutions are coupled. The optimal Q depends on expectation computing with respect to optimal Q2. So the optimal Q1 here really depends on expectation of Q2. And the optimal Q2 depends on the expectation of Q1. That's why these kinds of settings don't have the optimal solution. You have to iterate through up until you converge to some point. Right? So it's not like you have a fixed solution. Like, what's the optimal Q? And I just give you. In many cases, you have to cycle through the variables up until you find the optimal ones. And it's guaranteed to converge because we've shown that when you're optimizing with respect to one of these factors, it's a convex optimization problem. You can find the solution. So it's a coordinate descent, and you guarantee that after every single update of Q, your variational bound goes down. Okay? So you cycle through the variables in turn and update them until some notion of convergence. You typically say if they don't change by some epsilon, you've converged. No, I think my PowerPoint crashed again. So, right? But in our case, notice what happens. In our case, something interesting happens. If we look actually, it turns out that taking an expectation of Z1, because we start with the Gaussian distribution, is actually equals to mu1. And expectation with respect to Z2 is just mu2. We can actually compute these things exactly for this case. So we can solve it in one step, basically. And notice what happens is that the green is our Gaussian, the red is the mean field approximation. Okay? So the red corresponds to factorial approximation over the two random variables. So that should come as no surprise, right? If you have a multivariate Gaussian and you're looking at the product of individual factors, your approximation is going to be axis-aligned, basically Gaussian, right? So here, this is what the approximation looks like. And then one observation to make is that the factorized variation approximation tends to give you approximations that are compact. So one question is this a good approximation? Why can't your approximation look like this and cover more mass, right? But mean field approximation just chooses the approximation that's compact. It sort of sits inside your distribution. There are also other alternative forms of KL. And notice that this is something that we can compute in closed form. We can cycle through and compute what these factors are, right? And that's the whole idea behind mean field approximation, because you can actually find an approximation. So we've looked at the variational approximation that minimizes KLQP. But suppose that we were minimizing KLPQ. That's another form of optimization you can do. It doesn't really fall out from the variational bound arguments, but in principle, you could do this optimization if you wanted to. So suppose we're minimizing KLPQ. I can write down what the KL is. It has this form, just by definition of what KL. This is the definition of KL. This is a constant term that doesn't depend on Q, right? We're optimizing with respect to Q. It doesn't really matter. And it's easy to show that if you try to optimize this property, that the optimal Q, by optimizing this, is just going to be the marginal of P. Right? So the optimal factors are given by the marginal distribution of P. And so the way you can think about these two approximations is that if you look at the KLQP, your Q distribution is going to be compact. It's going to be sitting inside the green approximation. If you're optimizing KLPQ, your approximation is going to be spread. Because if you look at the marginal probability, what's the marginal probability of this green Gaussian? Well, the marginal probability here is going to look like this, and the marginal probability of this is going to look like this, because it's covering these both of them, right? So your approximation is going to be too spread out. And there are some approximations like there's things called expectation propagation that's trying to optimize this scale. And the variational bound arguments and in mean field approximation, you get approximations like this. Okay, depending on what the problem you're trying to solve, you can use either one. So it's interesting. It's interesting to look. So why do we get this compact representation? So let's look at the form itself. The difference between these two approximations can be understood as follows. Let's look at this particular form. There is a large positive contribution to the KL from regions of Z space where PZ is nearly 0, right? Unless QZ is also close to 0. So let's parse this out. If PZ is 0 and QZ is very large, you're going to have a huge contribution to KL, right? Because think of it, like if PZ here is like 0.0001 and QZ is 0.9, this is going to be a very big negative number. And if PZ has some mass on it, then it's going to be a big positive number. Right? So for example, if my Q would like put a lot of mass over here, notice what happens. If Q has a lot of mass over here, then its contribution, this is going to have very small number. This is going to be a very small number divided by something big or something, not that small. It's still going to be a small number, right? So log of the small number is going to be a very big negative number. And if its contribution has positive, it's going to be a very big negative number. Minus minus is going to be overall big positive number. So when we think about this, minimizing KLQP leads to distributions QZ that avoid regions in which P of Z is small. It really is set up, basically, you can't assign probability to the regions where the true posterior has small mass, small probability. So it only focuses on the regions where it has a high mass. On the other hand, let's look at this one. Q assigns almost zero probability here. Well, if Q assigns almost zero probability here, that's okay, because this is very small, right? So even if this is large and this is very small, because this is very small, it's not going to contribute that much to the overall KL term, right? So it's a balancing fact that basically within the family of distributions you're considering, it's always going to try to find regions where P of Z, your true posterior, has some mass. Right? That's why you end up in these solutions. On the other hand, if you look at the KLPQ, you've changed the distribution, right? It's expectation with respect to P, log of Q over Z. Then it really needs to assign, like if it doesn't assign any probability to this thing, P of Z is going to have some probability assigned to here. And if this doesn't assign any probability, Q doesn't assign any probability over here, if Q doesn't assign any probability to the green space, then you can see that Q value is going to be very small. But on the P, it has to be, the contribution to the KL term is going to be large. So the overall KL term is going to be large. So in this case, you're forcing Q to really cover the whole posterior, right? So that's why, you can just simply analyze and you can basically say, okay, what happens if Q doesn't assign high probability over here? You have a huge KL term. What happens if Q assigns high probability here? It doesn't really matter, because it's expectation with respect to P. If P has 0 here, it doesn't really matter what Q is doing there, right? So it's really trying to basically, minimizing KLs, you lead to distributions that are non-zero in regions where P of Z is non-zero. Even if it assigns some mass to places where P of Z is 0 or close to 0. So now what happens in the multimodal distributions? So let's say you have two distributions with a unimodal one. Then if you look at KLPQ, it will try to spread its mass over all the modes, right? If you look at KLQP, it will have to find a single mode, just explain this mode, right? And just ignore the other one. So if you look at both of these, so both of these methods behave very differently depending on what the task and what the problem you're trying to solve. On one hand, if you look at KLQP, you're explaining this mode, you're completely ignoring the other one, which is bad, right? On the other hand, if you're looking at KLPQ, you're covering both modes, but what's wrong with this distribution? No. It's not accurate, because look what happens. What happens is that it assigns its highest probability in the places where your true posterior has the smallest probability, right? You have two modes, two bumps, and there is no probability in between. This approximation will basically say, no, this is the most probable one, right? Because it's to cover all of these distributions. So it will most likely assign probabilities in the places where the true posterior doesn't have a lot of mass, right? So that's why dealing with multimodal posteriors is generally very hard, right? So people are trying to come up with the sampling methods. There is importance weighted. So for example, in variational autoencoder, if your posterior is, or in deep belief networks, if your posterior is multimodal, mean field approximation will just find one mode, which maybe in many cases it's okay. It's like you look at it and you say, you know, it could be a car, it could be a shoe. And your variational inference said it's a car, period, right? So that's the reason to think about this. Or, depending on how you initialize your mean field, it might capture a different mode. So depending on the initial conditions, you can find one mode or the other mode. That's why mean field inference is not, it's not convex. It really depends on where you initialize your model, how you initialize your model, because you can find one mode or another mode. But in many cases, in most of the cases, the way you define a mean field approximation, it will just capture one mode. It's not going to capture both modes. And maybe the true posterior will often be multimodal. So there's a bunch of different works people are trying to figure out. Maybe your posterior should not be just a simple Gaussian or a simple, factorial approximation. Maybe it should be, a multivariate, or not a multivariate, but multimodal distribution. Maybe it should be a mixture of 10 modes. And there's a lot of work people are trying to do that. So KLQP will tend to find a single mode. KLPQ will average across all the modes. So you get to choose your own. There is also a class of so-called alpha family of divergences that's defined this way. I don't have any intuition for that equation, but there are 3 points about this equation. That's where mathematicians come in. If you let alpha go to 1, it will correspond to doing KLPQ. If you let alpha, which is a hyperparameter, going to -1, KL would correspond to QP. So depending on your alpha, you can sort of blend between finding a single mode versus averaging over the modes. When alpha equals to, this family of divergences, it's positive, non-negative for all alphas, and it has the same property. It's 0 if and only if Q and P are the same for any alpha. So it's a richer family of divergences, and if P of X is fixed and we minimize this family with respect to Q, for alphas that are big negative, the divergence will be zero forcing. It will underestimate the support of X. It will really try to just focus on high probability mass of P. For alpha that are bigger than 1, the divergence will be zero avoiding. It will really try to stretch distribution and cover everything. Right? So depending on the applications and what you're doing, you can use this family. There's also one other thing that people typically use. For alpha equals 0, you obtain a symmetric divergence, which is called Hellinger distance, which has this form. So this is symmetric. If you set alpha to be 0, KLPQ and KLQP, they are the same, which in some cases might be useful. Sometimes you see papers optimizing this divergence. So let's see, remember how we've done it in the case of deep Boltzmann machines. Remember we looked at the variational inference. So let's just revisit what we've done. So you're approximating intractable distribution with a simple attractive distribution Q, parameterized by some parameters mu. So again, log, you multiply, you divide by Q. Q is our recognition network. Think of it as a neural network. You use Jensen's inequality. And then again, something interesting happens. You take the expectation with respect to Q. You have log of the joint. This is something that you can compute. The partition function, remember, in Boltzmann machines moves out, so it becomes a constant, plus the entropy of Q. It's exactly what we've seen. And it's quite interesting because you don't need to worry about partition function. It's something you can't compute. Has nothing to do with variational parameters. That's why you can optimize these variational parameters, right? And now you have to take expectation with respect to these random variables, right? And this is the variational bound. And again, it's just the same way as the marginal minus KL divergence between Q and P. So And you maximize KL between approximating and true distribution with respect to these variational parameters mu. Okay? So it's exactly the same thing as we've seen, just applying this theory to this particular model. And if we look at this variational valve and we choose a fully factorized distribution where we're basically saying, in this case, we are specifying what the distribution is. We're not really deriving, even though I think that you could derive, you're basically saying it's a fully factorized family over all hidden units. And the probability that the hidden unit takes value 1 is going to be given by this parameter mu. And the probability that hidden unit takes value 0 is going to be given by 1 minus mu. And we're going to be optimizing with respect to mu's. Right? And if it's exactly what happens if you just plug it into the variational bound, you can compute expectations, you can maximize this with respect to the variational parameters mu, and you end up with a set of fixed point equations. Exactly, if you trace back with respect to expectations, you plug this in, you take an expectation because everything is independent. If everything is independent, you can break the variational bound in the product of a bunch of independent things. And you can optimize each independent thing separately. Right? And so you're optimizing for layer 1 unit J has this update. So for all the J's, like if you have 100 units, you have 100 of these mu J's. And then level 2, you have hundreds of these mu K's. And level 3, you have hundreds of these mu sub M's. Right? And so now you can cycle through all of these equations up until some convergence. And what happens is that you will reach some approximate posterior. Typically, if you run these updates for 5 or 6 iterations, they will converge to some approximation to the posterior. Now, these Q's are specifying new posterior. So now, this is my approximation to the posterior. Right? Does that make sense? So this is not the same as to say that your true posterior has a bunch of independent variables. This is just saying you're finding some approximation to the true posterior which has these independence assumptions. So it can still model, a single mode quite reliably, right? And this posterior will change as you update the parameters of the model. So once you have new parameters, new theta will give rise, so new theta, you have these new parameters of the model that you're training. And once you have new parameters of the model, your approximation to the posterior is going to be different. So every time you do gradient descent update steps, you update the parameters, your posterior changes. You update the parameters, your posterior changes. And the posterior is necessary. You need to use these ones to actually do learning of parameters in the model. Okay? Any questions? Yes?
So, I think the K and divergence amounts to focusing heavily on the tails of two probability distributions, right?
On the tails?
Yeah. Because we want to ensure that if one probability is close to 0, the other is close to 0.
So if you look at the KLPQ, where Q is the true and KLPQ and Q is approximation, then yes, you want to focus on the tails. You want to cover as much as possible. So you're going to spread your mass to cover the P distribution, even though you're going to assign a lot of mass in the spaces where P has 0 probability, or close to 0 probability. Right? The mean field will try to find, it's a compact, it will try to find an approximation that covers a single mode, right, or sits inside the distribution. Right? And as I mentioned, you can look at the alpha divergence family where you can control for that. You can say, maybe I don't want to just cover this. Maybe I want my approximation to be like this in this case. Right? Depends on what your goal is. The issue of covering everything is that your approximation can put a lot of mass, in particular in high dimensions, it can put a lot of mass in regions where P is just 0. Mean field will only focus on places where P, your true posterior, has non-zero probability. But it might ignore other regions where P has a lot of probability and you're just not going to see that. So it depends on what you want to do. In many cases, there are techniques where people are trying to, and we'll see some of these techniques. One thing that you can do, and some papers on that, is that you can try to do approximation like this, but then you can use something that's called importance sampling, which is you sample a bunch of samples from this distribution, and you see how probable these samples are under your original model. And you do reweighting, right? So for example, if you get samples here, under your original model, your model will say, no, these are not probable. But if you get samples from here, so yes, it's probable. So you can do reweighting, but this is where it requires to do some form of a sampling to kind of cover that. Or there are some approaches where, again, as I mentioned, you can make your Q function to be more elaborate. Your Q function could be another stochastic model that basically is able to carve out multimodal space. But then the problem is that learning becomes difficult. Because if your Q function is complicated, then how do you learn this Q function? So yeah, it's a chicken and egg problem. You have to have a Q function to do learning of the parameters of your original model, right? And so you update your Q, you update your P. You update your Q, you update your P. And so now it's a chicken and egg problem, because if your Q is complicated, you have some bad approximation. How do you update P? Right, so we'll see some examples of that. So for the next class, we're going to look at the alternative way of doing inference here. In particular, we're going to be looking at MCMC-based methods, Markov chain Monte Carlo-based methods, and sampling-based methods to approximate the posteriors. And then there is some interesting work that combines both variational and sampling. So you can think of variational as a very quick way of finding some approximation to the posterior, and then you can initialize your sampler from that posterior and then try to do sampling based approaches that that would attempt to move around in the space and sample your modes in a more reasonable fashion. Let's see. Okay.